We're going to talk about parent functions and their transformations today. This is one of our most important videos and lessons of this class. What we learn in this lesson we will use for the rest of the year, pretty much every chapter, almost every lesson, over and over and over. So sit up straight, change your posture, get your notes out, put your finger on that pause button, eliminate your distractions, and do those things every video anyways, not just because I'm giving you this pep talk. There are different classes or categories of functions that are important. Linear, quadratic, absolute value, and square root are 4 examples, but there's many, many, many. And what this class does is it basically takes a class of function, analyzes it, determines how it behaves, how it's useful, how to work with it, and explores how that class of function, what we can do with it. So for example, a linear function has a parent function of y equals x, or f of x equals x. Fx means y. This is the basic, boring, stripped-down, plain version of a line. Right? We have all sorts of lines with y equals mx plus b, where m changes your slope and b changes your y-intercept, but all of those can be thought of as some transformation or some manipulation of this line here. That's the parent function. There's a parent quadratic, which gives you this parabola, y equals x squared. A parent absolute value, y equals the absolute value of x. Absolute values make a v, whereas quadratics make a u. And a square root is like a parabola on its side, and also cut in half, y equals the square root of x. These are 4 examples, but there's many, many, many more of parent functions. So we'll talk about transformations to absolute value functions in detail in this video. F of x equals the absolute value of x is the parent function of an absolute value. It makes this v. The reason it makes this v is if you plug in negative numbers for x, like if I were to do f of negative 3, well that becomes the absolute value of negative 3, which is just 3. Absolute value just makes things positive. I'm not sure why that 3 isn't appearing. There we go. So we get 3. And negative 2 gives you 2, and negative 1 gives you 1. But if you plug in 0, it just stays 0, and plug in 1, you get 1. It doesn't switch signs, it makes things positive. So wherever we had something that started negative, it became positive. Things that were already positive stayed positive. And 0 is sort of the point where all that switches, because 0 is neither positive nor negative. That was the crux of this. That's why this little corner point or vertex happens here at the point 0, 0. Well, we can take this parent function and manipulate it. We can do things to it. For example, I could take f of x and do f of x minus 3. And what f of x minus 3 does is it takes all of the x values, all the y values, and subtracts them by 3. So here's f of x equals the absolute value of x. But now I'm going to subtract 3 from all these, because it's f of x minus 3. And I'm going to get 0, negative 1, negative 2, negative 3, negative 2, negative 1, 0. It gives me a graph looking like that. It's the same graph, but slid downwards. This new function is called a translation, a vertical translation of the original. So you slide things up or down, and it's a translation. This minus 3 on the outside of the function sent it all down 3. Everything that you do to the equation, you have a predictable outcome. In this case, subtract or add something to the outside, you move up or down. Next, we can add or subtract something to the inside. Here's f of x minus 3. Well, this graph is going to do kind of what you think it might, and also kind of the opposite. You might be thinking, since this one moved it down 3, maybe this moves it left 3. It actually moves it right 3. And explaining why it moves it right instead of left isn't terribly difficult, but I actually leave it for an extra credit problem in this chapter. So if you're in my class and doing this, we'll explore why this moves it right 3 instead of left 3. You can get points for that. And if you keep kind of following along with this video and having that in your mind, you might even answer that question as you go. But part of the idea is, there's f of x, but now these numbers weren't manipulated because we weren't subtracting it from the whole y value. We were subtracting it from the x value. So everything got moved to the right 3 instead of left 3. It'll always do the opposite when you're inside that little function hole. Next, 3 times f of x. This is multiplying the y values by 3. So the parent function now gets kind of squeezed. We call this a vertical stretching, if you want to think of it that way. All the y values are now 3 times as high, because again, this graph over here is just the graph of f of x equals the absolute value of x. Sorry, this table. This table is just the parent function. But now all the y values are getting tripled. So 0 doesn't change, but 3 becomes very different. So we had the point 39, which would be way up here, but the point 0, 0. All the y values are tripled, which causes it to increase faster. You know, it's like we used to have the point 0, 1. It's now the point, sorry, 1, 1. That's now the point 1, 3. And it grows much, much, much faster. This is called a dilation. A dilation changes the steepness of the graph, or it affects the y values without affecting the x values. It's also often called a vertical stretch, or vertical shrink, or vertical compression. I'm not going to use those terms. I say this was dilated by a factor of 3. Finally, we can flip the graph with a negative in front. So now this is a negative f of x, and what that does is it takes the graph and it reflects it over the x-axis. It's called reflection. Because, again, all the y values are being multiplied by negative 1. Oh, that's a bad color. Multiplied by negative 1. Negative 0 doesn't really mean anything. It's still just 0. But they all start pointing down instead of pointing up. This is a reflection over the x-axis. The 4 possible transformations can be represented with a, h, and k, where a, h, and k are things that you add, subtract, and multiply into this function. The a value affects the dilation, and it affects the reflection. So if a is not 1, there's a dilation, which with absolute value is actually like a slope. Like if a is 3, then this line would have a slope of 3. If a is less than 1, it also gives you, less than 0. If a is negative, you have a reflection. So the a value affects the dilation and the reflection of the graph. The h value moves things right to left. If it's negative, it goes right. If it's positive, it goes left. And that's very, very confusing, but there's so much of it in this class, it'll become second nature to you. The k value moves things up and down. Stuff happening to the outside of the absolute value affects the y values. Stuff happening on the inside affects the x values. So here we have an a value of negative 2, an h value of positive 3, not negative 3 but positive 3, and a k value is 4. The h value is positive 3 because you take positive 3 and plug it in here, and that gives you x minus 3. So this graph was moved right 3, up 4, and then it was reflected over the x-axis, so it's going to be pointing down, and it has a dilation factor of 2. So the slope is basically negative 2, down 2, right 1, down 2, left 1. Again, that slope thing only applies to absolute value. So let's graph a couple here. The parent function is graphed in yellow. That's just y equals the absolute value of x. We're going to explore what happens to this function as we change it. This dilates everything and gives it a slope of 2 instead of 1, so it now starts moving like this. And then this moves everything left 5, because right now our a value is 2, our h value is negative 5, because you have to do the opposite of what's inside those absolute values. So everything got moved left 5, which means I could just take this first point and go 1, 2, 3, 4, 5. And now the slope was 2, so I go up 2, right 1, and up 2, left 1. And there is my new graph. This is my g of x. Note the domain is all real numbers. The range goes from 0 to infinity. Okay, look at this and see if you can determine what a, h, and k are. It's always a good idea to start problems with that. And then if you actually want to just pause and graph the whole thing or work out some idea of how this would graph, that would be worth doing. The a value is negative 3/4. The h value is 1, not negative 1, and the k value is 3, not negative 3. Just this term, just this value is the one that switches. So this is going to translate, right? Well, first, 4 things are going to happen. It's going to reflect over the x-axis. It's going to dilate by a factor, I wrote the word a there twice, by a factor of 3/4. It's going to translate right 1, and it's going to translate up 3. Those are the 4 transformations taking place. Translate right 1, translate up 3. So it's going to start by pointing down. Then it's going to start scaling by 3/4, and then it moves right 1 up 3. So what I can do instead is just go to the point 1, 3. This right here is my new corner point, or my new vertex. And then from that point, I can do a slope of down 3, right 4, and down 3, left 4. About there, probably gonna be a little bit off. That is my new absolute value function, translation from the parent function. Back here, I didn't really list out the changes. It was a dilation by a factor of 2, and a translation left 5. We can explore these things with Desmos and with graphing calculator also. You can always graph by plugging points into a table. The tough part can be knowing where to start by plugging points into a table. That's where the whole plugging stuff into a table breaks down in this class. You don't always just want to do from -3 to 3. That might not get you the interesting stuff in the graph that you need, and by interesting I mean the vertex. It might not get you the critical points. What you always want to do is think about, what should I plug into the middle of the table? What should I plug in here to make this equal 0? Just that little piece, and that's 2. And I can plug in numbers above it and numbers below it, and then plug in the points. So I plug in a 2. 2 minus 2 is 0. The absolute value of 0 is 0. Times 3 is 0. Plus 4 is 4. That's a 0.24. I plug in 3. 3 minus 2 is 1. The absolute value of that is 1. Times 3 is 3. Plus 4 is 7. We have a slope going like this. Plug in 1. 1 minus 2 is -1. Absolute value is 1. Times 3 is 3. Plus 4 is 7. You can only just plug in points to a table and graph it that way. It's going to be longer, but will help you if you're confused, or is a good way to check. Because I can go to point 2, 4, that's my corner, my slope is 3. This graph's going to go like this. But you have other options also. On your graphing calculator, press y equals. I'm going to do 3 times the absolute value. To get absolute value, press second 0. And second 0 pulls up your catalog, which has a trillion useful things. The first one is abs. X minus 2 is, I'm going to type in now, the absolute value of x minus 2 plus 4. I can graph that with this top right button. There is that graph. And then I can press second graph to pull up my table and check to make sure the table looks like I want it to. And it does. With 2 in the middle, you get all the same values I had before. A third way to do this, in a really fun way, in a lot of ways, is to do it on Desmos. Now, Desmos is a internet app, iPhone, smartphone app. You can do this on your computer. I'm going to be typing stuff in with my keyboard, y equals, and I could type in what the actual equation was, which was 3 times x minus 2. Here's the absolute value button right here. 3 times x minus 2. I'm going to press to the right to get past that absolute value, plus 4. And it gives me that. But another useful way to do this is just type y equals a. Don't put a number in, but to put a letter that isn't x, y, or z. So y equals a times absolute value x minus h plus k. It asks me if I want to make these sliders, add sliders, a, h, k. I really do. That gives me a, h, and k right here, and here is the graph it's functioning, or graphing. So if I move h around, it gives it a horizontal translation. If I move k around, it gives it a vertical translation. And I'll put it there. And then if I move a around, it changes the dilation. When it's negative, it points down, positive points up, and I can get it to match that 3. There it is. Now we have the same graph. I'll pull this down. You could also just type in numbers if you wanted to. I could make it a 4, make it a 5, make it a -2. If I wanted 3. So you can graph this by Desmos also. There we go. That's going to wrap up our video for today. You take care of yourself. Hey, thanks for watching. I hope that was helpful. If you have any questions, leave them in the comments down below. There can be questions about the video you saw here or anything else in math I'm happy to help with. Subscribe if you'd like to watch more videos or see other updates as they come. I'm going to try to run through all of Algebra 2 Trig and then eventually hit more classes like Algebra 1 and Geometry and Pre-Calc and everything else. If you have questions about stuff covered that's not in this video, still let me know. I'm happy to help. And finally, if you're not one of my students taking the class, but you found the video and are watching it, or maybe you're a teacher and are watching it, you can buy the curriculum and buy the worksheets to go through it. That's found at the website listed down below also. So again, thanks for watching. Have a wonderful day.